ML, or machine learning in EventTracker, our quest for anomalies. So machine learning is a substantially overhyped term these days. It means all sorts of things to all sorts of people. Maybe it means self-driving cars, or it means a computer program that plays chess at a very high level. None of those things. We're in the log management business, and so therefore we're referring really to unsupervised machine learning, more specifically as it applies to time series. Log data is inevitably bound up with time, and so our machine learning is all about detecting anomalies within that time series data. This is a result of 3 or more years of development here at EventTracker. And for those of you that had earlier versions, V8, V7, we used to refer to this as behavior. For those of you in the UK, yes, there is a U there, but I am speaking to you from America, so it's behavior. And the whole design has been one that makes it very simple for the junior analyst to use and benefit from. Of course, if you happen to be a power user, then you can extend machine learning and its jobs as part of EventTracker in all sorts of interesting ways. So what problem are we seeking to solve with machine learning? Well, log data or machine data is being ingested by EventTracker in really large volumes. And we have to think about how to solve the known unknown problem, right? What is the known unknown problem, by the way? It's the fact that there are certain conditions that we know to be problematic, but then given the very large volume of data, it's difficult to know or to be on top of when it is that these conditions might occur. Now, anomalies, or out of ordinary as we used to call it, observations can be a leading indicator of trouble. But again, that extremely large volume makes it impossible to touch in any kind of manual way. And then the static alerting that we had as part of EventTracker from version 1 winds up being insufficient. It doesn't adapt to new models in the data. It doesn't think about seasonality. It's so rigid that it tends to be sometimes more trouble than it's worth. And so therefore, machine learning becomes interesting. How do we do machine learning anyway? It's done by jobs. These jobs are defined by us at the factory or by you if you're a power user, and they operate constantly in the background. What do? Well, they look at the log data that's coming in via the data feeds, and they look for or detect anomalies in order to bring this to the attention of the analyst. So, hey, Mr. Analyst, wake up. Here's something unusual going on in this data feed that we see. You should probably investigate it and check it out. The analyst can then explore these anomalies and then find out what the factors are that influence the reporting of such anomalies. Why do we do all this? Well, obviously, knowing that we have a problem somewhere is a fine thing, but being able to understand specifically why it has occurred and what's influencing it is, of course, orders of magnitude better. Now, the machine learning implementation in EventTracker is self-learning. Remember we said a junior analyst can benefit from it? Yeah, so the user, as you may well be one, don't need to specify these algorithms. You certainly don't need to curate any of this stuff. You don't need to bother adjusting these machine learning models or some, obscure data science property in order to get the benefit of it. As new data is ingested by EventTracker, the machine learning models that we define will actually adapt themselves. Why is this important? Well, because data feeds have seasonality. What does that mean? Well, data looks different maybe over the weekend than it does over the weekday, maybe after hours than it does during hours, maybe over the spring versus the summer. And so the self-learning is important in order to be adaptive to the fact that what's normal, what's ordinary, what's routine might in fact be changing over time and not be static. That's one of the reasons those static alerts don't really quite work well. At the end of the day, machine learning populates these things called models. And what is a model? It's a self-contained artifact. In our case, it happens to be schema in a table. What do they contain? They contain historic information in a condensed fashion as to what's happened around a particular anomaly. What's valuable about this is that in order to access and explore, if you will, this model, you don't need to go back and look at the raw data and re-index it in any way. These models also evolve up to the last bucket, and we'll learn soon what the concept of a bucket is. And they're adaptive. So as they see seasonality, as they see changes, you can see what the differences are and what we consider to be an anomaly. So if you're going to be working with EventTracker's machine learning, it's time to learn some concepts. And these are very common concepts when we're using same terminology as we'll get in the industry, particularly from the Elasticsearch people. So let's look at some of these terms. A data feed. What's a data feed? Well, it's nothing more than a source of log or machine data. For instance, syslog streams are data feeds, as are data coming in from our Windows sensor, from our SNMP V1, V2, or V3 receivers, from Office 365, from VMware, from files that we might be receiving to process, and so on. So data feeds can be both real-time, as syslog and the Windows sensor will give you, and they can be batched. That is, they can be an IIS W3C file or a log file that's delivered to us maybe once a day. So these are all data feeds. Next concept, machine learning job. What's a job? Well, a job is what looks at that data feed, and then after matching and extracting and processing the data, populates something called a machine learning model. It is this model that ultimately drives the display that you see in EventTracker, and also the alerting. Hey, Mr. Analyst, wake up. Something unusual has happened. We're getting a lot of hits from this particular IP address to our website would be an example of a job output. Anomalies. Well, Webster says an anomaly is something that deviates from what is standard, normal, or expected. So how do we define anomalies? Well, we extract specific fields via the machine learning job, and then look at the frequency of occurrence. How often has this happened? To compare against thresholds and to report an anomaly. Hey, Mr. Analyst, wake up. We see that there are too many account lockouts occurring in the enterprise, much more so, maybe 50% more so than what is normal given what we have learned over the last 2 weeks. That would be an example of an anomaly. An influencer. So when we extract fields in the machine learning jobs, in order to identify an anomaly, an influencer is something that is the value of this extracted field. Let's take an example. Let's say we're getting a lot of login failures that are occurring, and they're occurring primarily because two particular accounts are failing all the time. One's a service account and the other is a user account. One's being actively exploited by some sort of hacking job, and the other has had a failed password, an expired password, and is continually and constantly causing these login failures to occur. The influencer then in this case would be the username. One would be the service account that's failing because the password's expired. The other would be the user that is getting hacked, as an example. So these two influencers might cause an anomaly as it relates to number of login failures that are occurring in the enterprise. And then we have this bucket and bucket span. These are important concepts, folks. A bucket is nothing more than a mechanism, a period of time by which we divide the continuous stream of data into batches for processing. We're getting data all the time from syslog, from Windows, from SNMP, from Office 365. By analyzing data in buckets, we can more easily see whether there have been any significant changes. And then we get the benefit of smoothing, right? Some of the random fluctuations get smoothed out. If you choose shorter bucket spans, when anomalies can be detected more quickly, and alerting, of course, can happen faster. But then you become kind of sensitive to variations or noise in the data, and you might get a lot of goofy, false positive kind of alerts. By the other side, choosing a very long bucket span can be a problem in that if there is an anomaly going on, it can get smoothed out, and also it might take longer for you to get the alert. Let's take a look. Here are, three bucket spans against the same data. You see a spike has occurred right there in the center, but then different bucket spans. At the topmost part of the chart, you have a 1-minute bucket span. What happens here is you can see the anomaly very clearly, that red line in the middle, but you can't quite see the periodic trend, right? So that's a little painful because it's interesting and useful to see the periodic trend. On the other hand, in the bottom chart, you can see the periodic trend pretty clearly, But then notice you can almost not see the anomaly. It doesn't seem to be much of an anomaly. It's the span in the middle, the 10-minute span, that tends to be the best for this particular sort of data. You can both see the anomaly right there in the middle, as well as you can see the trend pretty clearly. I remind you again that alerting is something that can get affected by the bucket span, and so selecting a bucket span is an important thing. Luckily for you, this is all done by us as part of the software. But if you're a power user and you're looking to define your own machine learning jobs, then bucket span is something that you should certainly pay attention to. So what's the anatomy of a machine learning job? We said jobs are the ones that run constantly in the background, and they ultimately populate a machine learning model with data. Well, they all have a name, and they have a bucket span, as we saw, that they operate with. They invariably use an anomaly detector. An anomaly detector in EventTracker is always a number. That is the frequency of occurrence. Now this number can either be specified, hey, if I ever see more than 10 logon failures in this bucket span, of 30 minutes, that's always a problem for me. You could specify that. Or you could say, there is seasonality. There are more students logging on in the fall and in the spring than there are in the summer and over the Christmas break. So then I don't want to specify a number like 3. Why don't you go learn? And whatever you learn is going to be the threshold. And an anomaly is if you get, a 50% variation above or below, if you like, the threshold. So this is an anomaly detector, and it's something that's part of a machine learning job. The job also has one or more matching rules, which it uses to identify entries in the data feed against which now it can apply these extraction and analysis rules to extract the relevant fields, thereby apply the anomaly detector. In the example that we just saw, you might look at logon successes or logon failures rather, and then identify the username as being the field and the frequency of occurrence of the total number of logon failures in a bucket span, and the influencer would be the username. 2 kinds of jobs are supported, single metric and multi-metric. In single metric, you consider only one field for anomaly detection. For example, how many total HTTP requests have I got? I don't care if they're gets or they're posts or they're anything else. I just want to know the total number. And then that total number is what I'm using to decide whether I have an anomaly, yay, nay. You also have multi-metric jobs, which consider more than one field for anomaly detection. An example is user location affinity. I am worried that a user might actually log in to a location or a target machine which he has never logged in before. So if Susan constantly logs into workstation 5, why then that's okay. We learned that behavior is normal. And one fine day, if she's suddenly logging into SQL Server 6, which she never did before, and so multi-metric, the user, Susan, and the location, SQL Server 6, that combination is considered to be an anomaly, and that's a multi-metric job for you. Here's how machine learning works. You define a machine learning job, and then you activate it. As part of the machine learning job, there is the definition of a bucket span, let's say 60 minutes. There are matching rules. So the job then runs constantly, looks at the data feed in question and says, do I have entries in this data feed that match the rule? Yes. In the example we're taking, we're going to say the data feed is coming from, say, an Active Directory machine via our sensor, and the matching rule is to look for Windows login failures. In a 2008 domain, this would be easy. You get events of ID 4625, and so that would be the matching rule, right? In the real-time feed coming from the Active Directory machine, look at all of the data. If the event ID is 4625, why then you have a match, and that's something I'm interested in. So then, now that I've found it, a 4625, what am I looking for? Well, I'm using an extraction rule to identify the field of interest. Who is the one that's failing to log in? Okay, so that's the username. And we can surely find that pretty easily because all 2008 R2 and higher have, those nice XML representations. So finding the username that failed to log in is an easy thing. We now can apply the anomaly detector in the bucket. As we're processing it, let's say it's a 60-minute bucket. How many of these login failures have we observed? because each time we're getting a login failure, regardless of who the user is, we're incrementing the total. And so if we're saying that normal number of login failures for this organization, as we learned over the seasonality, is say 3 in a bucket span of 60 minutes, why then have we seen more than 3? And if we did, how much more than 3? Let's say that our variation setting was 50%. So we needed to see maybe 5. And if you see 5 login failures in 60 minutes, why then you have an anomaly. So now you must populate the model with data for visualization and then issue an alert if such an alert is configured, saying either I'm seeing an anomaly, hey, I've seen 5 login failures where I normally see 3, or I might also have a login failure for something first time seen, that is, I'm seeing user Joan login, fail login for the very first time, never saw her fail login before. That's a problem. So what's new in version 9.1? After all, if machine learning was called behavior and was available in version 8 and earlier, what's new in 9.1? Well, the big thing is, in versions prior to 9.0, machine learning was only available on an instance basis. For those of you that are Essentials customers, what that means is it was only available to the master MSP. In 9.1, machine learning is now available on a group basis. That is to say, it is available to the sub-MSP and quite possibly to end customers as well. That's a big deal in version 9.1. Also worth noting, for those customers, particularly enterprise customers that are using the collection point collection master model, the machine learning components that are being provided fully support that model. So we can roll up for enterprise customers either on an instance basis if you're selecting the old style of working, or on a group basis if you want to enable that functionality. We provide a variety of machine learning models with Essentials for all sorts of Windows events, including the ones that you see: software install, USB, Windows logon, IP address, location affinity, logon failure. And the idea here is to be able to detect all of these anomalies and then report them on a group basis. If you are a enterprise customer, why then you not only have these 7 models, but pretty much anything that our team can concoct for you across many products, not just Windows, and across all sorts of data feeds, including SNMP, including syslog, and pretty much anything else. We're releasing machine learning, or re-releasing machine learning then. And in which versions might it be available? Well, it's available in 9.1 and higher. It is available to you if you are a EventTracker Security Center, that is to say a license-only buyer. So if you're a self-serve buyer that purchased the software and are operating it yourself, if you are in maintenance, you can get machine learning by upgrading to 9.1, and there is no additional cost. If you're a service customer, maybe you've selected EventTracker SIEMphonic or SIEMphonic Enterprise, you can choose to get this implemented for you by the ECC on either an instance basis or on a group basis. There is no additional cost since you're already having the subscription for EventTracker. Of course, your instance must get upgraded to 9.1 to get this, but there is no license fee. If you're a SIEMphonic Essentials or an EventTracker Essentials customer, and this is the most exciting of all news, you can now get it implemented on your instance. Of course, you must upgrade your instance to 9.1 on a group basis. That is to say, it can be multi-tenanted and apply the rules independently for each of your sub-customers. Since you are in maintenance, if you have the EventTracker Essential services, there is no additional cost to you either. So let me demonstrate how machine learning actually works, and we'll take a look at a job, its definitions, the overall settings for machine learning, including enabling it or disabling it. We will walk through a model and explore what that model has to offer using the Model Explorer, how an analyst can pivot from that information to search, and then of course add it to a case so that we can co-manage this for you between our team and yours if you happen to subscribe to the service. So now that you've understood the terminology of machine learning, let's take a look at machine learning in action. What I have here is an instance of SIEMphonic Enterprise, and I have a variety of machine learning jobs that I have specified. In particular, I'd be interested in looking at Apache traffic. So the company happens to have an Apache web server, and it is facing the general public. And so there is a seasonality to the traffic. Traffic ebbs and flows, busier on weekdays, less so in overnight. And so therefore there is not possible for us to define hard and fast rules. And yet we're always interested in examining this traffic. So let's take a look at, for example, request methods, which tell us what sorts of methods have been requested. Are they gets, are they puts, are they posts, and how they are faring. Now, because the traffic ebbs and flows, static rules are difficult. And so we've said, go learn in a 3-hour window as to what's normal, and then evaluate traffic as it comes in over a 2-hour window. And if there's a variation of more than 10% based on what you learned over the last 3 hours, why then that's considered to be an anomaly. So as we explained, every job has matching rules. And in this example, we're receiving logs from Apache in real time via syslog. And the way we know they are Apache logs is because they have http:/1 in the description. And so the machine learning job would look at the data stream, that is the syslog feed, the data feed, and then pull out anything that matched. Once it pulled something out that matched, it would look specifically for the request method. And there are a variety of tokens that are available depending on what knowledge packs you've imported into the system. And the influencer, where are these hits coming from, is the source address, is what we're interested in. So now that we've defined the job and had it running for a while, if there is any out of ordinary behavior, why then I expect an anomaly to be floated up to me as an alert. And so I'm sitting here in front of the incident screen, and as I look at it all, I'm curious to see whether there has been any as a result of the request method. And sure enough, there has been one. As you can see, this is the request method anomaly. Well, to explore this, I would go down to the model for Apache request methods in order to take a look. And what do we see here? Well, we see that there are a variety of IP addresses that are hitting our web server in the last 1 day. And then the thing when I look at the anomalies, the one that jumps out at me are post methods. The get seems to be within reason. The head, the connect, these are all anomalous, but the total numbers that are troubling me like anything are the post. See, it's 103% variation. I normally get 32, and somehow I've gotten 65. Well, if the analyst wanted to investigate this, why then he could do a log search from here and take a look at all of the logs associated with that particular anomaly. Now we're interested to know where these things come from. And so when we expand the source IP, we see that a lot of them, 75%, are coming from some IP address that begins with a 194 and ends with a 199. All right, so if I were interested in understanding those, oh look, they're on Acme web server. And if I expand any one of these, I see that they have http:/1, which is why the matching rule worked. They are a post. It's against Acme, but they're coming from somewhere in Europe, in other words, somewhere in Austria. Gee, I wonder whether this is a bad IP address. To know this, I might go to the threats dashboard in EventTracker and see whether I have anything there that's been identified as an Austrian IP address. What this particular section of EventTracker is looking at all IP addresses from the outside and then comparing them against reputation. And sure enough, what I see is here's something from Austria, and it apparently belongs to Russian media. Now this is a problem. Why are they hitting my website doing funny amounts of posts? Gee, I wonder what some other threat intelligence source thinks about them. Let me look at IBM. Well, IBM says this IP beginning in 194, ending in 199, has a risk score of 10. So this is as dangerous gets. And what does this guy do? Well, he sends a bunch of spam. And he is Rus media, right? Russian media sitting somehow in Austria. Is it possible that he's actually sent us spam? Well, what targets has he worked against? So if I click here against the show, I can see that at 6:01 he sent something to our exchange box. Wait a minute. He's a bad IP address, famous for sending spam. He touched my website and then he sent something to my exchange server. Well, I can almost tell you what's going to happen next. So if we explore what he sent, what we see is that at 6 o'clock, he happens to have sent email to Harry at Acme, and it says, check your mailbox. Is it possible that Harry has fallen for this? So then let's hop back to investigate this, and sure enough, on workstation 1, there's been another attempt to touch that particular IP address. Expand this, and what do I see? I see that at 6 o'clock and 1 second, somebody has logged on. Who's logged on? Well, it's Harry. All right. And then what's he done? Well, 11 seconds later, he's run Outlook. Yeah, this sort of makes sense. That's the first thing you do when you get in. But then 30 seconds later, it looks like something called foo-modified.exe has run. And the parent process for foo-modified is Outlook. Oh my God, this site was known for sending spam. It sent something to Harry. Harry has opened Outlook, and Harry has, within the context of Outlook, run some other exe. Is it possible that this was malware and it was sent as a spam attachment? Well, let's find out whether the EventTracker EDR section knows anything about this. So here I am looking at processes that might have run that are unfamiliar, and I do see Acme workstation. And so if I expand this, I see that it is foo modified, that the user in fact was Harry, and it was in the context of Outlook, and it appears that it has communicated back out again to that 194 address. Gee, I wonder what VirusTotal knows about this. This is instructive because after all, I have antivirus running on the machine. If foo modified was malware, I expect that the antivirus has caught it, yes? Well, surely this is a Trojan because we see that 617 out of 56 antiviruses catch it as a Trojan. So if the company happened to be running one of these, for instance, Kaspersky or Malwarebytes, then this piece of software would have never been allowed to run. Unfortunately, the company happens to be running McAfee, and McAfee doesn't stop this. By the way, neither does Panda, neither does Sophos, neither does Symantec. Well, of course, neither does Trend Micro. We're not picking on any of these vendors. It's just true that not every antivirus, seeing it as it is based on signatures, can be 100% effective. So in this particular case, this line of defense has also failed. How did all this actually come about then? Well, how this came about was because we were interested in machine learning. In the kill chain methodology popularized by MITRE, you know that the first step attackers do is reconnaissance. And so what they were doing when they were checking out the website, the external facing website of Acme, was they were trying to find a soft target, one that would be susceptible to spam. And somehow they identified Harry and they sent him email. Because Harry fell for it, why then they got compromised. Acme got compromised on workstation 1. And now from the inside to the outside, which the firewall allows, traffic has occurred. Again, this is a threat from the outside, but this is something that your antivirus was powerless to defend against. Your well-configured firewall couldn't do much about. And it was the fact that we were tirelessly watching logs through a machine learning job that even though the attack actually occurred at 6 a.m., we were able to catch this. Without machine learning, without the process of looking at the logs, this would have been another instance where somebody got compromised, and then it might be much later, on average 9 months later, where you discover that there has been an infection and confidential data maybe is being exfiltrated. So machine learning at its finest, ladies and gentlemen, to the rescue. Thank you for your attention.